All right. So what I'll be talking about today is firstly just a quick introduction of our company. Then I'll talk about which factors influence an ADCS system design. There's often this decision that integrators of satellites face whether they should buy off the shelf or build it themselves. And I'll talk a little bit more about the pros and cons of each of those, and then some lessons that we've learned along with some interesting real-world examples. All right, so first off, our company is also focused on ADCS only products. Our first flight was in 2014. We've served more than 50 missions currently in orbit. We're located in Stellenbosch in the beautiful South Africa. We've delivered more than 1,000 products to more than 100 customers globally. We offer fully integrated ADCS solutions, so everything, including hardware, software, harnesses, ground support equipment, everything that you'll need, even a simulation tool for your ADCS. We also offer standalone components if you prefer the build-it-yourself option. Those include reaction wheels of various sizes, from 2U up to small microsatellites. The same goes for our magnet talkers. Then we've got some fine sun sensors, infrared horizon sensors in our Generation 2 product range, star trackers and magnetometers. There's a nice link about our Gen 2 product range. I believe it's a video. Please have a look if you receive the slides afterwards. Our facilities include an ISO Class 8 clean room and a dark room where we calibrate our optical sensors, such as the star tracker and our fine sun sensor. We've got a Helmholtz gauge to calibrate the magnetometers, vacuum chamber with thermal control, some thermal chambers in our production facility with humidity control. We've got our own vibration table, which was recently added, as well as a couple of staff that are IPC Class 3 trained. That's enough for the sales talk. I'll get back to the engineering, which I'm more comfortable with. So the first thing that I want to talk about is how requirements influence your ADCS design. What we've noticed is that different levels of requirements influence the ADCS design. So we've got the higher level emission requirements, then the derived system requirements, and then ultimately the lower level ADCS requirements. And all of those can in some way impact your ADCS design. And what we've noticed is that the typical top-down requirements model doesn't seem to work for the modern small sat or nanosatellite missions. It's not as simple as laying down requirements on a mission level, freezing them, moving over to system, freezing them, and then having a subsystem requirements, and then just building a system or procuring a system that meets all of those requirements. There are very often trade-offs and concessions that need to be made on all levels because the hardware just isn't out there, or we just can't build exactly what the mission needs. So ultimately, you'll work your way towards the ADCS requirements, come up with an ADCS design, but often you'll find that what is out there in the market or what you're able to build in the amount of time that you have won't meet requirements A and C, but it will meet the most important one. So we'll be willing to drop this one or make it less strict. So it's a very iterative process, at least in our experience. Then when it comes to component selection, once you've solidified the design, it flows down mainly from your ADCS requirements. You've got the decision of how many of each sensor once you've, for example, identified the need for a star tracker. Do you want to add a second one for redundancy? Do you have the budget to do that? When it comes to actuator sizing, your wheels and torquers need to be sized depending on your satellite size, the type of orbit that you're going to be in, the type of deployables that you'll have, the direction in which they're deployed, that will determine your in-orbit disturbances, which will affect the size of your torque rods. If you've got a very high slew requirement, so your satellite needs to be very agile, you'll need larger wheels with more torque or more momentum storage capability. And then something that I'm very excited about is component placement. That's where you get to work with the customer's CAD and really try to figure out a tailored engineering solution for their specific mission. So you've got, let's say, 5 or 6 different ADCS sensors, but you've also got a satellite design with a panel sticking out in this direction and an antenna sticking out in that direction. And you need to find a spot for each one of those sensors and make sure there's actually available panel area for a sensor to protrude through. You've got the sensor field of view to take into account, especially when you're using deployable structures. And then you've also got to take into account which ADCS modes does your payload require, does your antennas or your comm system require. So if you've got, for example, a star tracker pointing in a certain direction, but you've got an antenna which needs to face a ground station, will that star tracker still see stars, or will it point at the Earth when you point your antenna at the ground station? And those are things that not all customers seem to think of when they're buying or procuring their ADCS. And we've often seen that satellite designs need to be changed very late in the mission, just because these type of things weren't taken into account early enough. When it comes to the buy versus build decision, there are 3 main options. You can either buy the entire fully integrated system from a third-party supplier. You can buy standalone components and then build the system yourself. Then you've got to think about your software that's going to run the system. That, I believe, can also be outsourced. I'm sure there are companies out there that do that. And then you can build the entire system yourself. So from the ground up, build everything, or at least most of the components yourself. In this decision, there will be various stakeholders. So on the lowest level, you've got the technical stakeholders. If you cannot find an off-the-shelf solution to meet your requirements, you'll obviously want to go for the build-it-yourself solution if you've got the technical capability to do that. From a commercial perspective, the company might want to push outsourcing rather than vertical integration, which will lean more towards the buy decision. And then you've got, of course, the programmatic stakeholders, which will push timeline the most. And if your timeline simply does not allow a self-build option, then you have to go for a buy option. But in principle, there are 3 main factors when deciding whether to buy or to build, and that's risk, time, and cost. Unfortunately, I can't provide a nice one answer or one-liner for whether or not you should buy or build. Every mission is different, and there are pros and cons to buying versus building. I'll start with the pros of buying. The first and most obvious pro there is that you'll leverage years of ADCS experience, not only from the supplier, but also from other customers that have flown this supplier's ADCS. It's in most cases the shortest lead time, and there's virtually 0 development cost. There are cons to buying a system. It's not always optimized for every mission. The suppliers generally build a generic solution which can fit most missions, and it's not tailor-made for your specific mission. And you're going to be dependent on a supplier, 1 or more suppliers, which is not necessarily always a good thing. Then you could argue that there's a higher cost per system versus building it yourself, but then you're not taking into account the massive NRE, the non-recurring engineering cost that you'll have to incur when you build it yourself. There are good things about building an ADCS yourself. You can tailor make the system for your specific mission. You've got no dependency on any third party if you choose to build everything yourself. And it's a very, very nice vertical integration strategy to get all of that development in-house if your company supports that strategy. But there are, of course, cons to building it yourself. I've mentioned most of them. You'll firstly require a whole development team, ADCS engineers, electrical engineers, mechanical engineers, and software engineers. Those are all the components that make up an ADCS. The development time is usually in the order of years if you've got a very narrow solution that you're working towards. It could be less than a year, but it's usually in the order of years to develop a full ADCS for a larger mission. You've got massive investment, so non-recurring engineering And there is, of course, increased risk because you'll build something that's new, which has a very low TRL. There are many options out there, and you'll be wise to choose carefully. Things to consider is reliability and what the TRL of the system is, and whether or not there's evidence, so qualification reports, in-orbit reports, the reputation of the supplier in the industry, which other companies are using this system or the supplier, if you can find information like that out there. How stable is that supply chain? How long is the lead time, not only for one or two off, but if you expand your company and you start ordering 10 or 20 or 50 units at a time, can your supplier handle that? Will they still be around for your next mission? It's also a question you need to ask yourself. And then most importantly, does the integration into your mission of that system make sense? You'll have to take into account mechanical integration. How does the system get bolted onto your spacecraft? What's the electrical and the software interfaces? Are those configurable at all? And how much effort is it going to be on your side to accommodate that system? Which ADCS modes are available? Can that be expanded? If you've got a very custom control mode that you want, can your supplier implement that for you? And how easy is it to operate the system? Then something that you'll thank yourself later for is checking the support structures of the supplier. How well is their documentation? How much support equipment do they give you, both hardware and software? And how can they support you during commissioning and operations of your system? I'm listed cost here on the right, but I put a little band sign on it, because even though cost of ADCS systems are fairly large, and you'll want to go for something that's cost effective, all these other considerations are much more important than cost. You'll end up spending a lot more in man hours if you don't pick a supplier that meet all of your needs in these other areas. Then just lastly, some lessons that we've learned in the process of building an ADCS. And we're recently, with our Generation 2 product line, come across this quite often. And that's, if it's new, it usually takes longer than you expected. So it's good to always add margins. And that includes when you're building your own spacecraft, adding margins for lead time from suppliers, adding margins for testing your ADCS and calibrating it on ground, if it's something that you're doing for the first time. And lesson we've learned as well, hire good project managers to make sure everything happens on time and everything is taken into account when you're planning your project. You rarely get it right the first time if it's something that you're doing that's new. Allow for mistakes to be made, and add a margin or extra buffer into your timeline for additional design iterations. And I cannot emphasize testing your system enough. Test it for race conditions, for edge cases, test it in a realistic in-orbit environment. And that ties nicely in with my last point. You must have a simulation tool if you're going to be building an ADCS. You need to know how your algorithms will interact with the space environment, how it will interact with the satellite body. And having a proper simulation tool that can tell you what your modes and your configuration will do under certain conditions is a must. During test and integration, we've also learned a couple of lessons. I'll just quickly run through those. So there's a very big misunderstanding in general about the concept of an ADCS coordinate frame versus just your normal mechanical CAD frame. We often see customers not taking into account that the ADCS has its own built-in coordinate frame, and it, with its own sensors, has a certain knowledge of how the satellite is oriented in orbit, and what does zero roll pitch and yaw mean to the ADCS. And that's not necessarily the same as your X, Y, and Z definition of your mechanical CAD of the satellite. So make sure you know what the translation between your frame and what the ADCS thinks the frame is. The most important sensor of your satellite is the magnetometer, except for your payload, of course. But in the ADCS, that's by far the most important. If you don't have something like reaction thrusters to desaturate your wheels, you need to use magnetorquers to desaturate your wheels. If you don't have a proper magnetometer measurement, you can't use your magnetorquers properly. Magnetometers are easily disturbed and disrupted by sources such as solar panels, fasteners, your EPS, electromagnetic valves, and which is why we normally recommend a deployable magnetometer as well as adding a redundant magnetometer. And important, test your spacecraft in all operational modes. There might be a payload or a subsystem that's only used in certain scenarios, and it might generate a significant magnetic disturbance, and you want to make sure that you capture all of those operational modes when you're testing your magnetometer on ground. And if you're having, moving on from the magnetometer, if you're having deployable appendages such as antennae or solar panels, make sure that when you have sensors with a field of view, such as a sun sensor or a star tracker, that you don't have any of these sensors in their field of view. I know it sounds obvious, but we often see customers that don't take that properly into account. And then lastly, for test and integration, we've often seen problems with EMI. Those have to do either with ground loops, where different grounds, either from the chassis or the structure, or from antennae, are just connected at random with other grounds, and you eventually form ground loops, which firstly disturb the magnetometer, but secondly causes noise on power lines, which can affect components like star trackers in terms of its measurement accuracy. And then for EMI, we've often seen cases where long harnesses are used, and the notorious I2C bus of CubeSats is especially susceptible to EMI. There's a good example where a satellite designer had an ADCS on the one side, an EPS sort of perpendicular to that, with a harness running from the ADCS across the EPS to a magnetometer. And the magnetometer's measurements were continuously corrupted because of the EPS currents being generated and causing EMI interference on the harness. And the eventual solution was to shield the harness. So watch out for that when you're integrating and planning your cable routing in the satellite. Some learnings from in orbit. Adding margins to exclusion angles specifically for star trackers is a good thing. We've learned from some in-orbit images that the atmosphere is clearly visible in eclipse to star trackers. It's of course not intentional to take a picture of the Earth, but when you do take exclusion angles of the sun, the Earth, and the moon into account, it's always good to add a little bit of a margin in there. So with the atmosphere, instead of having the Earth's edge be your calculation point for the Earth exclusion angle, rather use the atmosphere, which in the images that we've seen is roughly 70 kilometers from the Earth's atmosphere that's actually visible in a star tracker image. Very faintly, but enough so to cause disruptions to the algorithms. It's very necessary to have a safe mode, especially for high spin rates. We've seen cases where multiple cases of satellites being accidentally spun up, either by an operator error, accidentally firing a thruster, and having an ADCS with a safe mode capable of tumbling from very high rates it could be mission saving. So take that into account. And then lastly, but I couldn't stress it more, check the polarities of sensors and actuators. In the very early days of our ADCS expeditions, we almost had a case of a torque rod being flipped in polarity, and luckily that was caught very close to integration. But make sure that you firstly check polarities of actuators on ground, but then secondly that you have the ability to swap polarity in orbit if that's ever needed. That was it from my side. If you do have questions, pop them in the Q&A section. I'll answer them as I have time. If you've got more questions, feel free to reach out to info@CubeSpace, and yeah, we'll answer them as they come in. Thank you very much for listening.